Hi everybody. Today, thank you very much for being here for the third week of ZUCCMAP. Today we are delighted to have Daniel, who is going to speak to us about stars and physics, and we are very happy about that. Good luck. The stage is yours.
Okay. Hello and welcome everyone to my ZUCCMAP talk. Just wait for a moment. Oh, perfect. PowerPoint's online. So my name is Daniel Gotsmann, and I'm in my last year of my physics bachelor. And today I'm going to talk to you about stellar spectroscopy and how we classify stars. So quickly to the outline of the report. I'll first be giving you a short introduction to a few basic physics concepts, such as blackbody radiation and absorption and emission of light. We'll then have a look at stellar structure and how we classify stars. Then we'll move on into the part that all the maths talks can't provide for you, experiments. I'll talk to you about the Astrowoche, where at the beginning of the year I conducted experiments. I'll show you my experimental setup, the results we gained, and finally draw some conclusions. Okay, so to start off, how do we astronomers actually observe and measure objects that are extraterrestrial? There's a few different ways we can do this. For example, by measuring neutrinos. This is a very high pixelated picture of the ice cube experiment, an ESA experiment in Antarctica, where they actually have a, I believe, 1 kilometer by 1 kilometer large grid, where they let measurement devices into the ice to cover an as large as possible surface, because neutrinos are actually highly non-interactive. We can also measure gravitational waves. So maybe you heard in 2017, for the first time ever, gravitational waves were able to be detected. And this is actually a proposed project by NASA, ESA, and several other space agencies to send a gravitational wave detector into space. And I'm really looking forward to this because we should be able to get great results. And also we can get very fancy, and we can actually go to objects and get samples that we return to Earth. So for example, we landed on the moon, or this is a probe that was sent to an asteroid passing near Earth called Bennu. It was launched, it flew to the asteroid, managed to land, grab a sample, and return with the sample to Earth safely, and that actually landed in November last year. Which is an amazing technological feat, and of course allows us to get very deep insights into materials present on the asteroid. However, with all these fancy technologies, it remains the fact that almost all the data we can receive from extraterrestrial object is measured optically, meaning light is emitted from some object, travels through space, and we observe them by eye or through a telescope here on Earth. So let's say we have light coming from such an object, for example, the sun, and we can split this up into a spectrum. So this is an example of a solar spectrum, where we see that actually for different wavelengths, we have very different intensity. So it's not a continuous spectrum, but we actually have certain peaks, and we have places where we actually have dips in our spectrum. And it's actually through this information of where the spectrum is not continuous that we can learn a lot of information about objects such as stars. Now, so that we can understand what information is contained in these absorption lines, for example, we'll have to have a look at some basic physics concepts to understand how light is actually formed and interacts with matter. So let's start off with blackbody radiation. So any object that has a temperature will naturally emit radiation. And what is most interesting about this is that it actually does not depend on the material at all. It only depends on its temperature. So the more we heat something up, the higher frequency wavelengths it will actually emit. And it does so following the Planck's law. So this is what a Planck curve would look like. So we see that we have a peak emitted wavelength, and then to the left and the right of it would be lower. And this is for a constant T. Now what happens if we actually change our temperature T? This peak will move to the left if we have higher temperatures and to the right if we have lower temperatures. So we simply take the derivative and try to find where the highest peak is. We actually find that the peak in the wavelength corresponds to, or is directly proportional to 1/T. So what does this mean? If we look at the light of, for example, a star, we can find where the highest peak or the strongest radiation comes from, and we can learn what its temperature is. And it actually turns out that stars are pretty good black bodies and follow this law. So this means blue stars are hotter stars and red ones are colder stars. Okay, next let's have a look at how radiation emitted by an object, for example a black body, interacts with matter. So Niels Bohr first proposed that the electron orbitals in around a nucleus actually have discrete energy levels and can only take these levels and they will not change. This means an electron will only be on a given set of energy levels. What this means is, for example, if an electron in an outer energy level here and wants to move to a lower one, it will lose energy, and this energy will be emitted in a photon. And a photon's energy is actually directly proportional through the Planck constant to its frequency. This, of course, also works the other way around. Aktio gleich Reaktio. We can also have a photon coming in that will excite an electron from a lower orbital to a higher orbital. What does this mean for us? If we have light going through a material, for example, a gas, it can be absorbed by the atoms, exciting the electrons to higher levels, and the light shining through will actually be weaker. So once again, moving to a spectrum. If this is a spectrum for the sun, and we actually see that the sun spectrum has several different lines where the light is interacting with matter in the stellar photosphere and is absorbed. Now, what is interesting about this is that because the energy levels are discrete and they depend on the element itself, this is basically like a fingerprint. So for each element, we can determine what these absorption lines will be. It's a very simple experiment. We set up a light source, we have the gas, and then we measure what light passes through. And through this, we can basically find these fingerprints. And then if we look at a solar spectrum, for example, we can determine what these lines are, and we can compare them to our catalog of fingerprints. And like this, we can determine through what kind of material our light has passed. Okay, so now let's move on to try and understand a bit more what's going on inside of stars and what kind of materials are present. So generally, stars form when we have a big cloud of hydrogen gas. And when this cloud gets large enough, it will collapse and it will form a star. Now, because there's a lot of energy when this cloud collapses, there's actually enough energy to start fusion processes. So hydrogen will fuse to form helium, and helium can fuse to form carbon, and so on. And this is possible because in nature, things tend to move to the most energy-efficient state. So helium core is actually a more efficient state for protons and neutrons to be in than a hydrogen core. However, this does not continue indefinitely. Actually, we look at the energy per nucleon. So a nucleon is protons or neutrons inside our nucleus. We actually find that there is an optimal element, which turns out to be iron. So for lighter elements, fusion processes are most energy efficient. And from heavy elements, fission processes are actually more efficient. So for example, uranium, you probably know, can decay into lighter elements, and this will emit energy. So as a result of this, the elements inside a star that are doing fusion processes will actually always move towards iron, and we actually have an iron core in our star. So have another look at this, how this might look in a star. Of course, the heavier elements will always move towards the inside of the star due to gravity, meaning we have different shells of gases where different processes will happen. And the more light elements, such as hydrogen, will be on the outside, and the iron will be on the inside. Okay, now having looked at this, we can wonder, how can we classify stars? How are stars even different from each other? Now, the classification process of stars actually goes back even into ancient times. So the very first astronomers differentiated between stationary stars and wandering stars. Of course, nowadays we know that the wandering stars are actually planets, but this was already a first classification step done. Now, big strides were made in this regard during the 19th century. It was Joseph von Fraunhofer who first found that the spectrum of the sun has these absorption lines. Later on in the 19th centuries, it was several different scientists that actually determined the source of these lines and found that they corresponded to different elements. For example, Balmer was a Swiss scientist who first found the so-called Balmer series, which is a set of 6 absorption lines of hydrogen, which is highly important for stellar spectroscopy because hydrogen is actually very present in almost all star spectra, and hydrogen is the main building block of all stars. Later on, the Harvard system was introduced by a group at Harvard, and they took these polymer lines and said, okay, we'll just classify stars based on how strong the hydrogen lines are, with letters of 22 letters, A through V, I guess it would be, where A is the strongest hydrogen lines and V the weakest. This was later on refined by Anne J. Cannon. She simplified this to only 7 letters, O, B, A, F, J, K, and M. However, she decided to keep the letters of the previous system, so that's how we ended up with 7 random letters that now describe our stellar classes. This was later on refined again, so there's actually subclasses indicated by numbers. So for example, O7, the numbers are O through 9, and this actually describes the luminosity, but will not be discussed further in this talk. Exactly, and now let's move on to astronomers' very favorite diagram, the Hertzsprung-Russell diagram. So Hertzsprung and Russell decided to collect all the data of stars ever measured, and they plotted their luminosity versus the surface temperature. And what they actually found is that stars don't take up this whole phase space, but collect around certain areas. So 90% of stars are actually along this, what we call the main sequence. Then we have some giants and supergiants, and the white dwarfs down here. So as mentioned before, the classes O through M of the Harvard system correspond to the temperature. So the O stars are the hottest, and the M stars are the coldest, the red stars over here. Now, throughout its life cycle, a star will move through different phases of this diagram. So a main sequence star will grow old, and when the iron core gets larger and larger, and the hydrogen starts burning up, it would actually increase in radius and will form giants. And depending on how heavy the star was, this will either lead to a supernova, or they will just slowly cool off and form white dwarfs. Okay, now, so with all this knowledge we gathered, how light is formed in stars, how absorption lines are formed, and what kind of classes we can form, how do we actually analyze a spectrum? So this is an example spectrum of what we measured. We can look at the spectrum and we can try to find information about the star. So first of all, what we can see, for example, we have a nice envelope corresponding roughly to a blackbody curve, from which we can find the peak and through this, the star's temperature. But we can also see that we have strong absorption lines in certain areas, which we can try to match to the different materials. So I actually found this very nice graph here online, which compares the different classes. So once again, O are the hottest stars and M are the coldest stars. And as discussed, hot stars are more blue and the cold stars appear red on the night sky. And we can very clearly see in their spectra they have different absorption lines, and these tend to get more complex as we move to colder stars. So if we are not able to determine the temperature directly through a blackbody curve, we can actually try to identify these absorption lines, And the transitions between the classes are actually given by the relative strength or presence and absence of these absorption lines. So this can look, for example, like this. Flowchart I found in a source, where we can look at a spectrum and we can, for example, ask ourselves, do we see the sodium to H line and the K line? If we do, we move on through here, and then we compare what is brighter, the sodium K line or the H gamma line. And if they're roughly the same, that means we'll have an A star. Okay, now with all of this out of the way, let's move on to some experiments. So at the beginning of the year, I conducted some experiments in the Astrowoche. So the people of you who don't know the Astrowoche, this is something you can do in Practicum 3 of your physics bachelor. If anyone hasn't done Practicum 3 yet, I can highly recommend this. We went up to Diavoletza in January for a week to conduct measurements, several different groups doing different experiments, and me and my group doing stellar spectroscopy. So this is the view of us going up the mountain on the first day, and during all of this, I'm thinking, wow, I'm actually getting credits for this. So this is me and my group setting up our tripod. Anok is actually sitting right over there, enjoying the sunset on the first evening. This is us with our telescope doing a first alignment. And then we spent a few freezing cold nights in the dark looking at stars. So let's have a look at our experimental setup. We, of course, had our telescope, large tube with reflectors inside, and it was mounted upon a telescope mount. Now, why do we need mounts in experiments for astronomy? Well, as you know, the Earth rotates, meaning stars move across the sky. And if we are zoomed in very close on something, we can actually see this. So if we don't use a mount or disable our mount and look at a star, you can actually visually see it move out of frame as you're looking at it. So we don't want this because we actually want to take longer exposures, for example, of something. So we actually need to have the telescope moving against the sky, counter-rotating. And that's why we have these very expensive mounts that help us track the night sky. Then, sorry, I didn't find a better picture. We had our spectrograph. So this was actually mounted up from the top here to our telescope. So the light would go in through here. There is a slit in here where the light would be passed through, and then it would be reflected off a mirror here into our camera. The camera then took our measurement results. And to actually align the star with the slit, we had a small webcam attached here that we could always move the star to the right position. And then we also had a small neon calibration lamp. Now, why do we need a calibration lamp? Well, our raw data looks something like this. So you can see the light is split up into its spectral parts, but it's a black and white image. I have no idea what is what color. And each pixel value just corresponds to the number of photons measured. But I have no idea where what wavelengths can be found. So we have to do a calibration. So we took our neon lamp, put it on our spectrograph, and this has an emission spectrum looking somewhat like this with a very distinct, once again, I use the word fingerprint of neon. And we can just match this to a literature values and then linearly fit what pixel value in the y direction corresponds to what wavelength. Now, what kind of targets did we select to measure? So we tried to get targets for each different spectral class, because that was part of our task, to be able to differentiate between the spectral classes. And then these targets had to be visible at the time we were on the mountain. So this is a lovely little graph done by our colleague Etienne that gave a few select targets that during the nighttime would be visible and preferably would even be higher than 30 degrees inclination, such that we had as little interference with Earth's atmosphere as possible. Also, our great friend and helper through all this was Stellarium. If any one of you ever works with stars or just wants to find out what a certain constellation is, I highly recommend this app. It shows you where stuff is, what it is, and gives, for example, their stellar classes. Okay, let's look at some results. So once again, this is what our data would look like. We then process this by cutting off the top and bottom and then integrating across the vertical. And then we'd get something like this. Together with our calibration data, which would then correspond to the wavelength. Now we look at the spectrum, and we can see here, for example, the blackbody peak could be somewhere around here at 6.5 to 7,000 angstrom, which would correspond to about 4,500 Kelvin, which is a relatively cold star, meaning an M or a K star. And then we also see a few very distinct absorption lines here, here, these here, which we can correspond to our elements. Nicely demonstrated here. Now, what we can actually very interestingly see here, what we always have to consider during such experiments, is that we have very strong lines for water and oxygen. But now, careful, these lines are not necessarily from the star, because there's actually water and oxygen in our own atmosphere. And the light that comes to us from the star passes through our own atmosphere and actually interacts with it. So water and oxygen is probably not found in the star, but definitely found here on Earth. But what we can also see here is the H alpha and H beta, for example, the Balmer series mentioned before. And we also see heavier elements such as sodium and even molecules such as titanium oxide. So the presence of molecules strongly indicates that this is an M star, because in hotter stars, energy levels are actually too high for molecules to form. Let's have a look at some other stars. So these are several hot stars. Alnitak is an O star, moving on through to F star for Polaris. What we can immediately see is that it gets a lot harder to interpret the data. So we have a lot of noise, some frequencies in there. And for example, the blackbody peak is not always clearly distinguishable, and probably for the hotter one is actually outside of our measured range. Exactly. However, we can see there are very few strong absorption lines in the hotter stars. Once again, water and oxygen are present, but it's mainly helium and hydrogen that we are measuring off the star. Moving on to some colder stars. These are of classes M, K, and G. We can now more clearly see where the peak intensity is. What we can also see is Merak is actually the coldest star. The M star is that the peak moves from left to right, moving through to the colder stars, once again because for colder stars, our blackbody curve will move to the right. What we also see is that the absorption lines get a lot more complicated, which is because we have molecules, as mentioned before, and molecules tend to form more complicated absorption lines. And here we can once again see heavier elements such as magnesium or sodium. Now, after our first 3 nights measuring up on Diavolezza, we actually found that we have little more time left to conduct some more experiments. So we decided to take a spectrum of Jupiter. Now, this is a picture of Jupiter we also took. So we took a spectrum of Jupiter, and we can see once again hydrogen and oxygen. But what we can also see is we have methane. Once again, be careful, methane is also found in Earth's atmosphere. However, if it were so strong, we would have seen it in the other spectra. So we can actually quite confidently say that Jupiter has methane in its atmosphere. We then also took a spectrum of Jupiter's brightest moon, Ganymede, which is this one over here. Once again, here we see it's very noisy, and it's hard to specifically see a lot of lines. However, we see the few lines that we can clearly identify are also present in Jupiter. So we later on actually found out that Ganymede has a very high albedo, and actually most of the light we probably see from it is directly light from Jupiter that is reflected off its surface. Then we moved on and we did a measurement of the Orion Nebula. So the Orion Nebula is a big cloud of mostly hydrogen that can be seen at the night sky. It's actually relatively bright and can be seen through a simple telescope by eye even. These 3 stars here are of the dagger of the Orion formation, just below its belt. So this is actually quite large on the night sky. Now, what's the difference here is actually that it's not the gas that is radiating as a blackbody, but the gas is heated up by nearby stars, and this excites electrons to higher states. And when these electrons then move back down to the lower energy states, they will emit radiation. And this is why we get emission peaks and not absorption peaks, meaning they go up and not down. And we can very clearly see very nicely the different emission lines here for the Orion Nebula. So we have H alpha and H beta once again of the Balmer series. And we also see a little sodium and oxygen. So we know that the Orion Nebula consists mostly of hydrogen with a few heavier elements. And because we have heavier elements, we can say that this is probably actually the remnant of previous stars, because that's the only way that heavier elements could have been formed. Okay, so to conclude my talk, we had a quick look at blackbody radiation, found that the peak value actually depends only on the temperature. We had a look at absorption and emission and how absorption lines are like fingerprints for elements, which allows us to find what elements are in a stellar spectrum. So combining these two methods, we are able to categorize different stars into classes O through M, and we can actually learn a lot about their properties. These are my sources, and I'd like to thank you for your attention. Any questions? Yes, Kaspar?
Yes, so the tracker you used, does it rotate the telescope based on the coordinates that you're on and then calculates by how much it has to rotate, or does it use some kind of tracking image recognition?
Yeah, so the tracker has to know our exact coordinates and also the date and time. And we also have to align it. So this is a longer process. We first have to align it perfectly north. And then once we see stars, we have to do a second polar alignment where we take the North Star and center it. And then there's like a computer program that goes through different bright stars, points at them, and then you have to perfectly center them so that the computer can correct for any kind of differences. So we usually did like a 5 or 6 star alignment. And after we perfectly pointed at those, the computer knew, okay, based on this information, this is our exact orientation.
Okay, maybe a follow-up question on that. How sensitive was it to vibrations, like when you wrote around it?
Sensitive to vibrations was the question. So walking around it wasn't a problem. But there were a few incidents where we actually happened to break the alignment. For example, when mounting or dismounting our spectrograph, a slight knock in the wrong direction could throw off the whole mount, which could be quite annoying because you had to do the whole alignment again.
Okay.
Yes.
You said when you were calibrating, you used the lamp and then you used like shone the light through the gas, and then you measured the absorption like that to calibrate it. And now I wanted to ask, like, I mean, maybe it's obvious, but where, if you take this and then you look at this actual stars, what is the lamp that shines through the stars? Is it the star itself, where, like, that generates the light, that then gets absorbed by the star itself?
So the question is that the light travels through a medium and gets absorption lines. And the question is, where does this light actually originate in the star? Am I understanding that correctly? So I think this is a good picture. So the blackbody radiation coming from a star, it's the question basically where the blackbody radiation comes from, because a star is made up out of gas. So basically a photon created in the center of a star will travel through the star, but because there's such high energy levels, it will be constantly interacting with matter, being absorbed, re-emitted, and so on. And actually only when it gets to the outer layers is the medium optically light enough that it can travel through uninterrupted until it's at Earth. Now an interesting way we can actually look at this, let me maybe make a picture. So the blackbody curve we will see will correspond to the layer where the medium is thin enough optically that the light can reach us. And then we have our blackbody curve, something like this. However, if there's additional ways the material can interact with light, for example, by specific absorption of a certain energy level of an atom, this means the layer where that specific wavelength can actually freely leave the star is further out on the star, which means it's actually on a colder layer. So a colder layer means we'll have a different Planck curve. So let's say this is our frequency where it's excited. So the light traveling at this, not frequency, wavelength, sorry. So light traveling at this wavelength can actually only freely leave the star further out when it's colder, meaning at this range it will actually be down on this curve. So actually for a short time we go to a different Planck curve. And so this is a way that you can see absorption line being formed. Does that answer your question?
Yes.
Okay. Yes.
Can you re-explain how you get the intensity curve from the spectrum?
Intensity curve from the raw data?
Yes. Not from you get the spectrum from the star, and then like you build this intensity curve, and you really get that.
So how I go from this to this? Okay, so this is the output of the camera. The camera measures on different pixels just how many photons enter at that point. And then the spectrograph actually splits up the light beforehand, so the spectrograph actually looks that this is only of a certain wavelength on each different x-coordinate. And so first what we did is cut out the black parts to reduce noise. And then we took all the pixel values and we just integrated them over this axis. So we basically have a matrix with all the different values. We cut out the top and bottom parts of the matrix, set them to 0, and then we add up all the values in the vertical matrix components. Yes?
How is it that a particular x-axis corresponds to a particular frequency? Like, is this post-processed, or like because the camera wouldn't automatically?
No, exactly. The camera doesn't do this. This is actually done by the, let me see where I have the setup. This is done by the spectrograph, so a particular part of our experiment. So this part is mounted to the telescope, and it's passed through the spectrograph before it goes into the camera here. And the spectrograph has a slit, and through the slit the light is split up because it is diffracted differently depending on wavelength. Yes, please.
So you calibrated the spectrograph using this neon light.
Yes.
It looks like at room temperature, and then you carry the whole thing outside to freezing temperatures. Does the calibration still work?
Yeah, interesting question. So does the calibration work if we do calibration at room temperature and then move out to freezing temperatures below minus 15 Celsius? To a certain degree, this was actually noticed by us, and after the first night, actually all of our calibration pictures were taken outside directly at the telescope, so the camera was also already at the temperature as well as the spectrograph and everything else. Yes?
What type of difference did you notice? Was it noticeable?
I don't know if we specifically noticed anything. We didn't look at this because the data of the first night was just really not good. We had also had quite cloudy conditions. But for example, the sensitivity of the camera can depend on the temperature strongly. And of course, parts in the spectrograph that are of metal could deform with temperature and then cause different areas to be hit by different wavelengths. Yes, please.
Why are the cloudy condition a problem? I mean, it's like they pass through the clouds, or really just more water and oxygen in the measurement data?
So the question is, why are clouds a problem? First of all, the more clouds we have, the dimmer the light is that we get. So parts of the night we were actually seeing something through the telescope, but we couldn't see it by eye anymore. So there was significantly less light, which of course means the signal-to-noise ratio gets stronger. And as mentioned before, we measure our atmosphere as well, and then the lines, for example, water will become a lot stronger inside the spectrum. Kaspar?
Yes, I have a question about the graph you showed
slide 9.
Oh, no, sorry.
Not this one.
Maybe it was slide 7. No.
This one?
You showed like a picture of the spectrum, like the first spectrum you showed.
This one?
The first measured spectrum.
The first measured spectrum. This one?
Yes, exactly that one. So why are there, like, sometimes it looks like there are kind of two lines on top of each other.
Yeah, pointing out a perfect flow in our experimental results. No, so actually the range our camera could see coming out of the spectrograph wasn't the whole range the spectrograph covered. So we actually had to take 3 separate measurements for each spectrum for 3 parts of the light range. And then we had to stitch them together. Now it could be, for example, in this case, that conditions of the night sky changed between these measurements. And these were adjusted to a certain degree by adjusting the brightness. But of course, if there's suddenly a bit more clouds or a bit less clouds, this can change. And then you can see artifacts like this here. So this could be avoided, for example, by reducing the time done between the different measurements of a spectrum, or by just taking enough different measurements that you can average these factors out. Yes, last question.
Basically, we see the elements in the very outer shell of the star, where the light can emit.
Yes.
This implies we cannot see the really heavy elements because they're, as you said, they are in the core. So what's the heaviest element one can see in the star? Do you know?
We can actually see iron lines in stars, so it's not always a clean transition through these shells, of course. So especially in the lower temperature stars, we can see iron. What is actually more deciding on why we can or cannot see the elements is the temperature of the star. Because, for example, the hydrogen lines counterintuitively get weaker at the hotter stars again, not just at the lower ones, because a lot more hydrogen atoms are simply ionized. And if there's no electron, they cannot be excited. And similarly, it always depends on how much energy is required for this excitation state, and if there are actually any, for example, ionized or not ionized elements in the outer shells. Okay. One more.
How significant actually is the effect of like some parts of your spectrum getting drowned out by like significantly, I know, maybe more dominant sources of light? I mean, if you're looking at like the star, you have this layering thing going on, right? Sort of, right? You have this like very multi-layered data, right? Where you have like a lot of sources and you're sort of aggregating them. And I guess what I'm wondering is, do you know how much sort of precision you lose in there just through this aggregation effect, or like how much becomes unnoticeable?
So the question is, through these layers of a different star, if I understand correctly, how easy is it actually to determine where the light comes from, or what is the interference of the different sources of the different layers?
Yeah.
So I'm not certain on exact numbers, but I think it's actually quite easy to say there's a certain depth where most of the light comes out, and below that depth, the temperature and such, the energies are just so high that the interaction between photons and matter are constantly happening, and it's not actually possible for photons to freely pass outside of the star. So there was one exercise in our astrophysics series once, where we had to calculate the random walk time of a photon created in the center of a star. How long would it take to escape? And the answer was actually, I believe, in the order of years. So a photon that is randomly walking through the star and constantly being absorbed and re-emitted can actually take years until it leaves the outside of the star. So at that point, it will actually just have the properties of those outer layers. Does that answer your question? Okay, so thank you again.